Today's lesson's also going to focus on stoichiometry with a concentration on percent yield calculation. Our learning target for today is to be able to distinguish between actual yield and theoretical yield values, and then how to use those values to calculate percent yield. Let's begin by taking a look at both of these terms and understanding what they mean. Theoretical yield represents the maximum amount of product that can be formed given a certain amount of reactants. This value will always be calculated through stoichiometry. Very rarely will you be given this value. If you are given this value in a problem, it will state that the theoretical yield for this reaction is X number of grams. So it'll explicitly say what the theoretical yield is, but expect to calculate this the majority of the time. Actual yield is going to be determined experimentally. This value represents the amount of product that can actually or is actually formed in the lab. So usually a problem might state something like, in the lab 45 grams of product were made. So if that statement is expressed, then you should understand that 45 grams then represents the actual yield. This value is going to typically be lower than the theoretical yield for a product, and possible causes for this could be due to spills or incomplete reactions. We're going to use this synthesis reaction as an example of how to illustrate what an incomplete reaction would look like. So just to remind you of what synthesis is, if you have two reactants indicated here by a purple circle and a pink block, so a 1-to-1 ratio, you'll notice, of the reactants combines to form one single product. So in this case, our product is a block circle. You'll notice how the shapes form a union and that the color of the shape is a blend of the colors of the reactants. Now let's use that example to look at what an incomplete reaction is. So here we have 15 purple circles and 9 pink blocks. We can expect them to combine in that simple 1-to-1 ratio to form, hopefully you guessed it, what should be 9 block circles. That would be our theoretical yield. But in this case, you can see that we only have 7 fuchsia block circles that actually form. The 7 block circles represent our actual yield. If the reactants had combined in the expected 1-to-1 ratio, we would have theoretically achieved the 9 block circle products. So you can see that we do not have the maximum amount of product that this reaction allows for. There are different reasons for incomplete reactions. Some of the reactants may never have come into contact with each other. For example, there may not have been a collision between this particular pink block and this particular purple circle. The temperature may not have been high enough. So if this was an endothermic reaction, for example, maybe the temperature was turned down too quickly. The hot plate was turned off too quickly. If the particles were in solution, maybe there was too much water and not enough concentration of particles to allow for them to come in contact. So in this case, we end up with 8 purple leftover circles and 2 leftover pink blocks. This diagram illustrates an instance of how actual yield could be less than theoretical yield. Now that we understand the terms actual yield and theoretical yield, let's examine percent yield and see how we can calculate that. In the chemical industry, the aim is to achieve a high percent yield. The higher the yield of a reaction, the more economic the process. There will be less waste to dispose of, And not only would that save money, but it would have less of an impact on the environment. High yields could also mean less energy is used, and that's another way of saving money. Research chemists in the chemical industry are always looking for the most efficient or cost-effective method of making a particular product. And so to calculate percent yield, the mathematical relationship of that is the percent ratio of the actual yield to the theoretical yield, as shown in this equation, actual yield divided by theoretical yield times 100. Now let's examine the question, can percent yield ever exceed 100%? If this were to happen, that would mean that actual yield is greater than the theoretical yield. Let's look at this picture to understand a reason as to why this may occur. If we were to look at this gray-brown liquid opaque mixture and assume that these are products of a chemical reaction and the samples being poured into this filtration setup onto the filter paper to separate the brown precipitate from the liquid. If somehow the brown precipitate mass, which is the actual yield, appears greater than the theoretical mass, it could mean that there is still some liquid present. In addition to being filtered, it may need time to dry in a desiccator or in a drying oven to make sure all of the liquid has evaporated and is not being included in the measurement of mass. So this is showing you that the presence of contaminants by the excess reactant or water, it could be even water, could cause the mass to appear greater than it actually would be if the product were pure. On the other hand, if some brown precipitate were left in the original beaker instead of being poured out into the funnel, then the actual yield would appear lower due to loss of precipitate. Also, if there are side reactions happening, other products could form and also impact the value of the actual yield. Now that we've gone through these terms, let's go through an example to see how to apply our knowledge. You can see at the top, I've given you the formula for percent yield, as well as some clues or hints to remind you what theoretical yield and actual yield mean. The first step is to write and balance the following equation. So why don't you pause the video and take a moment to write out the reactants and products for this equation. Did you get this equation? Great, now take a moment to balance it. So hopefully you notice that you need a coefficient of 2 in front of the first reactant. So let's go ahead and place that there. And then to balance out the bromines, 2 times 3, that's 6. So we'll need a 6 here in front of the potassium bromide. And then finally, to balance out the potassium and the sulfur, we will also need another coefficient of 3. Now that we have a balanced equation, we can begin the problem. So the first part of the problem states, if I perform this reaction with 35 grams of cobalt-3 bromide and an excess of potassium sulfide, that means you're not going to run out of potassium sulfide. You have plenty of potassium sulfide. Theoretically, how many grams of cobalt-3 sulfide should I be able to make? So let's identify what we're given. 35 grams of cobalt-3 bromide is this right here, this compound that I'm underlining with my laser pointer. And we are looking for grams of cobalt-3 sulfide, which is this particular product right here. So let's take a moment and set up our dimensional analysis table with the given value. On the whiteboard, I've written out the balanced equation and also the pathway that we are going to take. So in the problem, we're given a mass of the reactant. We will be converting that to moles, setting up the mole ratio. Remember, every stoichiometry problem has the mole ratio step. And then finally, because we're asked for mass, we will be converting to grams at the end. Since the first step of our stoichiometric setup involves converting to moles of the given value, you can see that I've set up my labels so that grams cancel. Take a moment to calculate the molar mass of cobalt-3 bromide and write that in the correct spot. Hopefully, realizing that there's three bromines here, you would know to multiply that by its molar mass of 79.90 and then add that to the mass of cobalt, which is 58.93. We're going to round all of our masses to the hundredths place. That's how many grams are in 1 mole of cobalt-3 bromide. So we have successfully converted grams of cobalt-3 bromide to moles of cobalt-3 bromide in this step. So the first step is done. The next step now is to convert to moles of our product using the mole ratio. So take a moment to see if you can set up the mole ratio. Did you choose the right compounds for your mole ratio? So we're given moles of, or grams rather, of cobalt-3 bromide. That's the unit that we need to get rid of, and we're converting to moles of cobalt-3 sulfide. That is the product as shown here in the equation. See if you can plug in the coefficients in the right spot. Remember to use the balanced equation for the coefficients. Okay, so now that we've set up our mole ratio correctly, we're on to our final step of converting to grams of cobalt-3 sulfide. So take a moment to set that last step up. So let's just make sure you got the right mass for cobalt-3 sulfide, 214.04 grams in 1 mole. Now that we've set up our stoichiometry correctly, we are ready to solve using our calculators. So go ahead and multiply across, and then remember to divide the top from the bottom. Record your answer in significant digits. Pause the video so you can do that in your calculator. Did you get 12.5 grams of cobalt-3 sulfide? If so, you are correct. This amount represents the theoretical yield. So if we were to do this chemical reaction, given this amount of our reactant, 35 grams of reactant, we can expect to produce 12.5 grams of cobalt-3 sulfide. We know that we won't run out of the other reactant because in the problem it says that potassium sulfide is present in excess. Let's move on to part B. In part B, we have if 7.56 grams of cobalt-3 sulfide, so that would be the product here, are actually produced. So I tried to give you a hint letting you know that 7.56 grams represents the actual yield. When I conduct this reaction in the laboratory, what is my percent yield? Since we've already calculated theoretical yield and we're given actual yield, all we have to do is use the percent yield formula to solve. So we're going to do that now. For part B, and problems in the future, when using a formula, I would encourage you to write the formula out in its general form before substituting values. So for percent yield, our formula is actual yield divided by theoretical yield times 100. Now that we've written out the general formula, let's plug in our values. So the actual yield I wrote out here in red, 7.56 grams divided by the theoretical yield solved for in part A times 100. Go ahead and solve on your calculator and record your final answer. Based on our results, the percent yield of cobalt-3 sulfide comes out to 60.5%. Now let's move on to part C. If I perform this reaction with 50 grams of potassium sulfide, notice that is the second reactant, and got a 75% yield, how many grams of cobalt-3 sulfide did I make? So this time we're changing up the amounts and changing up the reactant. Okay, if there is no mention of the other reactant, you can assume that it is present in excess, meaning it will not run out. So just focus on the quantity that you're given of the reactant in the problem. Okay, let's set up our stoichiometry. Similar to in part A, where we were given mass of the first reactant, in part C we're also given a mass. So we need to convert mass to moles, and then using the mole ratio, convert to the product, the desired product, and then finally, because we're looking for mass again, convert to grams. So here I've written out the given reactant, 50 grams of potassium sulfide. Now we're going to set up our mole conversion. So go ahead and pause the video to do that. So in 1 mole of potassium sulfide, we have 110.26 grams of potassium sulfide. Now that we've completed the first step, we're going to move on to the mole ratio. Go ahead and set up your substances for the mole ratio. Remember, the moles of the given value that you want to get rid of in your stoichiometry setup go at the bottom of the mole ratio, and the moles of the product that you're looking for go up at the top. Now we're going to use the balance equation to plug in our coefficients. So for the moles of cobalt-3 sulfide, you'll notice there is no coefficient, so that simply gets a 1. And then down here for moles of potassium sulfide, we have 3 as our coefficient, so that's going to be 3 moles in that spot. Finally, now that we've converted to the moles of the desired product, we're going to convert to grams. So go ahead and set up your mole to gram conversion there. Did you notice how we had calculated this already in part A? So hopefully you were able to plug in the correct value for the molar mass of cobalt-3 sulfide. Now go ahead and plug all of these numbers into your calculator to solve and record your answer in significant digits along with the units and the label of the substance. Did you get 32.4 grams of cobalt-3 sulfide? Hopefully you did. And are you able to determine what this quantity represents? Is it the actual yield or the theoretical yield? If you guess theoretical yield, you are correct. We are not quite done with the problem yet, because if you read the question, we can see that we're given the percent yield, 75%. The question is actually asking how many grams of cobalt-3 sulfide will you make if you are expected to have a 75% yield in the lab with 50 grams of that original reaction. So all this requires is some simple algebra. See if you can set up your equation. Notice how this time, instead of solving for percent yield, we're solving for the actual yield. So now you just need to do the math to determine what the actual yield is. Notice that if you divide both sides by 100, you will get this expression, actual yield over 32.4 equals 0.750. Now all you have to do is multiply both sides by 32.4 to get your actual yield. So go ahead and do that. After completing the calculation, you should have gotten 24.3 grams of cobalt-3 sulfide as your actual yield. Now you are ready to complete the rest of the percent yield assignment.